On your quiz today, it's going to ask you what the scale factor is from one shape to another shape. So even though this format doesn't ask that, let's find out what the scale factor is that gets us from here to here. So what are you supposed to think of when you hear scale factor? Blank over blank.
Should go first.
Oh, yeah. Second over first. So grab a number from the second figure and grab a corresponding number from the first figure. Like 120. Which side does 120 go with? So we need to make sure, right? MS is listed first and second, or second first. What else is listed first, second? IL, LI, LI. Oh, something might have been wrong for you. So 120 goes with X. What does MI go with? MI is second, third, and LE is second, third. So yeah, do that. So the circles go together and the underlines go together. What is the scale factor? Second over first. Everyone go to your calculator and reduce that. 80 divided by 60, math, enter. You'll look at your calculator to replace it. 80 divided by 60, math, enter. What is it? 4/3. The shape is getting larger, so the scale factor should be greater than 1, and it is greater than 1. So the scale factor is 4/3, and now we need to find X. Alex, can you set me up a proportion to find X? All right, we're going to use this that we already had. 80 is to 60 as, finish off my proportion. 80 is to 60 as, well, you can't start with this one. You can't go from big to small and then go from small to big. You know what I mean? Yeah, there you go. 120 is to X. So we're just setting up a proportion by finding those corresponding sides. Please cross multiply. Jonathan, tell me what you get when you cross multiply. 60 times 120 divided by 80. That's how you cross multiply. 60 times 120 divided by 80. 90. So the missing side is 90. What? So you heard you? Well, it's bigger than 120. Yeah, so just remember those sides that go together. That's good. That's really good to look for the reasonableness of your answer. X is 90, and it did get smaller from 120. Yep. Very nice. All right. Can you measure it? All right, so throughout the history of warfare, combat engineers, did you know there was such thing as a combat engineer? Okay, good. Oh. They played a critical supporting role in war efforts. The primary task of the combat engineer is to facilitate the movement of friendly troops and supplies while impeding those of the enemy forces. So it's their job to decide where the troops go, when they go, and how they go. As a result, combat engineers spend time building structures such as roads and bridges to help move friendly forces while destroying those that could be used by enemy forces. Legend has it that there was a combat engineer who used geometry to devise a way to indirectly measure the distance across a river whose bridge had been destroyed. You can't just measure the distance across a river by he's not going to wade through the river with a measuring tape. You need some other device, a different way to measure how far it is across something that you can't really measure easily. He devised a way to measure the distance without ever crossing the river or even getting his feet wet. By determining the distance, he was able to devise a plan so that they could construct a bridge with the limited materials they had on hand. So there's a picture. This is mainly historical. I'm not sure if warfare works the same exact way nowadays. So we want to think of what are some distances that we could not easily measure physically. Like I could measure your height very easy physically. What are some distances that we couldn't measure very easily? The height of a building. What? The circumference of the earth. That's an awesome one. Okay, how far off the earth something in the air is, a cloud, an airplane, yeah. So those are things that we would measure them indirectly, not directly. Directly would mean the ant stands up and I get a measuring tape and I measure his height. But indirectly means I find the measurement without actually touching it, without actually measuring it. So here are some of my examples. I think we named most of them. Yeah, the height of a skyscraper. You're not going to scale that skyscraper and measure that. The distance across a busy highway. You could use indirect measurement to find that. And then the width of a river or a lake or something like that. In addition to what y'all said, those were good. So we're gonna use similarity, and we can find how to measure the distance across things that we couldn't actually measure. And you've been doing this in some of your worksheets already, but today we're really gonna focus on the word problems. All right, so go ahead and draw that picture in your notes or on your whiteboard, and pretend that you are that combat engineer, and you had to find out how far the distance was across that river. And the way that you did it is you measured distances on the ground. You sketched these similar triangles, and you measured this distance because you could, because you walked it, and you measured this distance because it was on the ground. And those similar triangles are going to help you find the distance across the river, the one that you didn't measure by hand. So this is just doing the same thing we've been doing, but now we're doing it with a word problem, technically. So you can see how long that bridge needs to be. Helen, how would we start this problem? What would we do first? Proportion, very good. Richard, set us up a proportion. Pick any number you want to start with, any of those numbers. Cool. 72 is to, class, which one does 72 go with, everybody? 30. 72 is to 30 as, now this part's important, Richard, now which one are you going to pick? 72 is to 30 as, you started with this triangle over here, you have to start with that triangle both times. Is to 30 as x is to 40. Very good. Okay, guys, you know what to do. Cross multiply. Raekwon, tell me what you get. 72 times 40, enter. Divide by 30, enter. What do you get? 96 what? Meters. Real world problems, word problems, deserve words in our answers. So it was 96 meters across that river. And you could actually find the distance without ever touching the water by making some similar triangles. All right, let's try another one. On a blueprint, this is what my husband does every day, and he told me that that's the real scale factor, so that's cool. On a blueprint, 1/8 of an inch represents 1 foot. If the height of a wall is 1.5 inches on the blueprint, what's the real height of the wall in the actual building? So like on the blueprint, you measure the height of this wall and you get 1.5 inches. I want to know in the real building, how tall is that wall going to be? Is it going to be tall enough for a tall person to walk through? Will it be too tall, too short? Let's use what to find out? Scale factor or proportions, either one. Okay? I'm going to teach you how to do it using proportions, but we'll also find the scale factor too. All right, let's do, write this on your paper. Let's do inches is to feet as inches is to feet. Because we want to stay consistent. We want to do the same both times. So if you go ahead and put your units down, that'll help you. Inches is to feet as inches is to feet. Let's write the scale factor that they give us first. How many inches? 1/8. Not even a whole inch. And how many feet does that equal? 1 foot. So 1/8 is to 1 as, where do I put this one? I already labeled this, that's nice. Top or bottom, where do I put it? Top, because it's inches. So this is pretty foolproof as long as you stick to a pattern. Inches is to feet as inches is to feet. And that's going to be how many feet in real life. I can't wait to find out if someone can actually fit through the doorway. How tall is it? Cross multiply 1.5 times 1, which is just 1.5, divided by 1/8. Be careful when you divide. You need to put that 1/8 in parentheses to protect it. We protect our fractions. We protect them with parentheses. Y'all getting 12? think that's a tall enough wall? Is 12 feet good? I wonder how tall that is. I think 12 feet is good. Do you know anyone that tall? I definitely don't. 12 feet would be the height of the real wall in the real building. Cool. Ooh. I think we're going to skip Lewis, that one. Sorry, Lewis. I'm going to skip you. We're going to go to Mark. Where are all the girls in these examples? Mark is 6 feet tall, but in his Facebook photo, he's only 4 inches tall. Here we go. There's the scale factor. What is the scale factor of his Facebook photo to his actual height? So we want to know how many times bigger we would need to, if we were blowing this picture up to make a life-size picture, how many times would we need to blow this up, how much bigger, to get his real height, to make it life-size? So let's find the scale factor. Scale factor, we learned, it's no different, is blank over blank.
Second over first.
Second over first. Thank you, John. Did you know? Thank you. Good. All right, so we want to put second over first. So we want to go from his Facebook photo, that's the first, to his actual height. So I'm going to put second over first. How tall is he? 6 feet tall. So that's my second over, what's his Facebook photo? First. Now, I'm not cross-multiplying. I am not cross-multiplying. So I just want to reduce that fraction. You can't reduce a fraction if your units don't match. So this is the only time, when you see scale factor, that would be the only time you would need to make the units match. If you're cross-multiplying, don't you dare change those units. Don't do it. What do you want to do? Let's change everything to inches. Do you know how many inches are in a foot? Think of a ruler. 12. Take that 6 and multiply by 12, please. 6 and 12. 72. So now, I hope you're writing this down, 72 inches over 4 inches. Look at that. The inches will cancel. And I want you to reduce that fraction. 72 divided by 4. What's the scale factor? 18 times bigger in real life. You would need to blow that up 18 times larger to get a life-size photo of Mark. 18. Oh, scale factors do not have units. Units canceled. The scale factor is just 18. Cool. If Mark is 2/3 inches wide in his Facebook photo, how many feet wide is he in real life? Let's just use our scale factor. All right, he's 2/3, and we're just going to blow it up times 18. Make sure you protect your fraction with parentheses. 2/3 times 18. These are fun because these are not as boring. We're actually using real world stuff. What'd you get? Is he 12 feet wide in real life? No, he's 12 inches wide. So how many feet wide is he in real life? 1 foot wide. So it's like he's as wide as a ruler. Makes sense. Right? Cool. Ooh, that's a pretty mural. The artist used a photograph to guide his painting of this American flag mural. He used a scale of 3.5 feet on the mural equals 1 inch on the photograph. What are the dimensions of the photograph? So what he did was he took a small picture. We don't know its size. We don't know. Then he blew it up larger and it became this, 14 feet by 21 feet. And we need to know what the dimensions were on the photograph. So we need to use this information to help us set up a proportion. We're going to do just like we did last time. Inches over feet equals inches over feet. Okay. So 1 inch is to 3.5 feet as, what do you want to do first, length or width? Have an opinion. Be opinionated. Length. Okay. So inches over feet equals, where do I put 21? The bottom. Because it needs to be inches over feet. It'll actually be wide, but it doesn't matter. Okay, go ahead and cross multiply. Setting up a proportion. Inches is to feet as inches is to feet. I'm going to let you find the other one by yourself. 1 times 21 divided by 3.5. 6. Find the other one by yourself, please. So it's 6 by something. Find this other one by yourself. Use the same proportion. 1 is to 3.5 as you fill out the rest. full-size photograph, right? Do y'all ever get pictures printed, or do you keep it all digital? So what are the different size options when you print pictures?
6 by 18.
6 by 3?
6 by 18.
I thought it was 4 by 6 or 5 by 7. I think those are the main ones. And this one, when you cross multiply, you should have gotten 4. It was a 4 by 6 picture. It was a 4 by 6 picture. What is the scale factor from the photo to the mural? How much bigger is that mural? That guy's Facebook photo was 18 times smaller than his real self. I want to know how much they blew up that picture to make that mural. We're going to use this right here, just like we did last time. This and this. Second over first. So I want the mural, 3.5 feet over 1 inch. Okay, good. Do the units have to match in the scale factor? Yeah. What do y'all want to do with 3.5? Change it to inches. Times 12. Everyone type it in. 3.5 times 12. Yeah. And it's just 42 to 1, right? So that would just be 42. 42 times bigger. That's a ton bigger. That's huge. Oh, it would take a long time to paint. All right, last one. Ooh, this was kind of on your quiz today. Last one, and then practice tomorrow. An ad campaign manager for McDonald's made some sketches for a billboard design on a sheet of paper. Which sketch will transfer the closest to a life-size billboard without changing the dimensions? Do you get what's happening here? If his sketch was not similar to the billboard, and they blew this up and tried to put it on the billboard, some of his ad might get cut off, and he would be in big trouble. You would need this to be similar to this, so that when you took the thing on notebook paper and you blew it up, it actually fit on the billboard. You're not going to change the size of the billboard. If it's already built and everything, you're just paying for the ad space. So how would we figure out which one of these is similar to this one? What did you do on your quiz today? Divide? You want to divide? Okay, let's divide. Let's see what the length to the width kind of scale factor is. What is 48 divided by 14? This is one way to do this. This is not the only way. So it's saying my length to width division must be about 3.4. So let's divide all these out. 11 divided by 1.8. What do you get? Yikes. I think this one's too long. Don't you think you went too long on that sketch?
Yeah.
That's too far. Okay, 6.9 divided by 2. Ooh, that's pretty close. 3.45. Yikes, that's really close. Let's check the next one. 9.2 divided by 1.7. Ooh, went too long again. Too long. And 7 divided by 2.4. 2.9. Which one is the winning sketch?
Second.
Yeah, very good. That